Welcome to lecture number 11, Information Extraction, in the course Foundations of Language Technology, winter semester 2020. To prepare to this lecture, again, what you can do is go to the slides and the code from the last lecture, and also you can read the chapter number 7 in the NLTK book, which we base our today's lecture upon. First, we start out with a brief recapitulation of what we did in the previous lecture. We introduced some evaluation metrics commonly used in machine learning, such as accuracy, precision, and recall. You can go to the definitions. Importantly, for the accuracy, what counts is the diagonal in such a confusion matrix. The confusion matrix sets the gold classes into relationship with our model predictions, and on the diagonal we have those cases where the gold labels correspond to the model predictions. So by setting this diagonal in relationship to all of the rest, we get the accuracy. Can also be interested in the precision. In this case, for a particular class, namely class number 3, we would take the third column into account. We would say that our model has predicted class number 3 twice, and it was true in one case, so the precision would be 1/2. We can do the same for the recall. In this case, we would say the true label, the gold label, was class number 3 three times, and we got it one time, so our recall is 1/3. We've also seen some very simple classifiers, such as the naive Bayes classifier, which uses Bayes decision rules and makes a very silly, in a way, independent assumption. But this silly independent assumption allows for an efficient classifier, but which then, of course, is not very, very strong in practice. We've also seen decision trees and the max entropy classifiers, along with others such as more recent neural network classifiers. In this lecture, as I've said, we're going to be dealing with information extraction, which both uses like programming and natural language processing ingredients. So we have 3 core questions. The first one is, how can we build a system that extracts structured data from unstructured text? So typically, if you go to the web or to some other knowledge source, the data is available in unstructured form, but we want to extract tables from such data, for example, because we can very conveniently work and very efficiently work with tables. What are methods that can identify entities and relationships in a text? Because then we can take those entities and their relationships and store them in tables. And this is also the relevant information that we want to extract, namely entities and their relationships. And which corpora are appropriate for our 2 tasks? How do we use those corpora to train and evaluate machine learning models? We will see answers to all 3 of those questions in this lecture. The lecture in a nutshell is, we have a lot of unstructured data. We want to use natural language processing to convert this into some structured form, such as like a semantic web which has entities and their relations stored. To give you a taste of structured data is typically a table where we have, for example, organization names and the locations which they are based in. So we set 2 columns in a table into relation, namely the column of organization names and then the column of location name, and the relationship would be in a company is located in a location. Once we have structured data, we can very easily work with this structured data. For example, to find all companies that are based in the location Atlanta, we could use that very simple Python code that goes over all the triples in our matrix, in our table, and gets all those entities E1 that are based in location E2. The kind of structured information that we have in mind comes in 2 forms: either entity type, so that we say like a specific entity, such as Angela Merkel, is of a specific type, such as she's a person, or Omnicom is a organization. And secondly, we also want to set entities in relation with each other, such that we have triples where we say entity 1 is in relation with entity 2. Both these kind of information can be complementary. Once we have the relation information, we know how entities interact with each other and how they are connected with each other. And this type information additionally gives us information that entity number 1 has a specific type and entity number 2 has another type. So let's make an example how we would extract structured information from our unstructured text and what could be difficult in such a case. So let's take this example here. BBDO South, which handles corporate advertising for Georgia Pacific, assumes additional duties for brands like Angel Soft toilet issue and Sparkle paper towels, said Ken Heldon, a spokesman for Georgia Pacific. While the latter company is based in Nevada, BBDO South is located in Atlanta. Let's assume this is our text, and now we have the question, where is Georgia Pacific located? And what makes the extraction of such structured information from the unstructured text is difficult is that we have a lot of different let's say company names or brand names in this text. So we have BBDO South, Georgia Pacific, Angel Soft toilet issues, Sparkle paper towels, Ken Heldon. So these are different entities in the text, which like kind of make it hard to associate the individual locations such as Nevada and Atlanta with the different entities that we have in the text. Secondly, we need kind of language inference capabilities, such as that we know the letter company, what does that actually refer to? Does that refer to Ken Heldon? Does that refer to Georgia Pacific, or what does that refer to? So that's a complicated thing, but how we're going to solve it is, or how we're going to hopefully solve it is, we're going to use information extraction. And to do so, we first need to decide the specific information that we're interested in. For example, are we interested in companies? Are we interested in brands? Are we interested in people, like in politicians, or in company associated personnel? And then the second thing is, once we know which information we're interested in, then we need to convert unstructured data, so this is the unstructured data, to structured information such as tables, which contain our targeted data, such as entities, the entities that we're interested in, and the relationship between those entities. So how we would typically process this in a classical natural language processing architecture is, we would have our raw text, which could be a string containing several sentences or a whole document. We would then segment our document into sentences, so that we get a list of sentences, each of which is a string. We do the tokenization, so each sentence is split into individual tokens. So we get a list of lists of strings, where each string is now a token. We do part of speech tagging that tells us whether each word tells us the word class of each word, such as verb, noun, adjective, and the other things. Then we detect the entities, so we work on a part of speech tag corpus. We detect the entities in there. From this, maybe we have a list of trees, depending on how we do the entity detection. And then we also detect the relationship between the entities. And we would get finally the relations, which is a list of tuples as we have seen, and the relations are between entities. So this is the classical NLP pipeline. It doesn't necessarily mean that people are still doing it like this today. So today, people oftentimes speak about end-to-end models, like they would use a neural network that takes in as input raw text and outputs the list of tuples, and you don't know what the neural network is doing inside. But so this is another approach that people have suggested in the recent years, but we will still go by this classical NLP pipeline, and that's the pipeline that we keep in the head when we as we process in this lecture, as we proceed in this lecture. So we already know how to do the first steps in the pipeline. So those first steps, right? So for example, we would take our document and we say do sentence tokenization. Then we get out the sentences. For all the sentences, we do the word the word tokenization in each sentence, and then we can also pause tag the words in the sentence, right? That's already what we know. So the next step that we'll be focusing on is entity detection. And entities are proper names such as Monty Python. We could also be interested in other stuff like the knights who say nigh. So this would be a noun phrase. And also sometimes entities could be indefinite nouns, or noun chunks such as every student or cats. So it really depends on what we are looking for, what kind of information we are looking for. But the common theme of the information that we are looking for and the common characteristic of those entities is typically that they involve something called nouns. And this is what we're going to be doing in the next few slides. We're going to be doing chunking, which is the extraction of certain phrases, and in the context of entities, we are particularly interested in noun phrases. And what chunking is doing, as you can see here, it takes some information and it breaks it apart into smaller units. Let's see how that would look like. Let's say we have a sentence such as we saw the yellow dog, and we now do this chunking, which is like a prerequisite for entity detection. So once you have chunked your text, it's also much easier to detect entities for you. Now we're gonna break it into three chunks, namely the first one is a noun phrase, we, and the second one is a verb. So it could be a verb phrase like saw, and the third one is another noun phrase, the yellow dog. And now in red we highlight all those chunks that we're interested in at the moment, namely noun phrase chunks. So as I said, the small boxes here are word tokens with part of speech. So we have the word tokens, each given with its part of speech. The larger red boxes are the NP chunks. And here also, as I said, there would be another chunk. This would be a verb chunk, but we're not interested in this. So let's look at an example of noun phrase chunking. So what we want to do here is we have this text, which I read out to you now. The market for system management software for digitals hardware is fragmented enough that a giant such as Computer Associates should do well there. So we have such a text. Now we want to identify the noun phrases, and you see they have already been identified for us. So first of all, we have the part of speech tagging. And then on top of this, we have the noun phrase information. So here the market is the first noun phrase, system management software is the second noun phrase, digitals hardware is the third noun phrase, a giant is the fourth noun phrase, and computer associate is the fifth noun phrase. So what we see from this, so chunks are often smaller than complete phrases. For example, the market for system management software, for digital hardware, is a single complete noun phrase. So that would be classified as a noun phrase in a syntax tree, for example. But we can or here it is divided into 5 or 4 different chunks. And chunks are often defined so that they do not contain other chunks. So we have a flat structure. So if we would take this whole thing here as one chunk, then it would contain those other chunks. So, and that's not what we want in chunking, but we want the smallest possible chunks typically. How can we identify chunks in NLP? So one approach to do so, there are certainly many different other ways, but one approach to do so is we define a regular expression or a small chunk grammar. And our grammar could look as follows. So we define it here. Everything that has potentially a determiner, 0 or more adjectives, and then a noun. We define this as a noun phrase or as a noun chunk. Then we look at this sentence here: the little yellow dog barked at the cat. We compile our grammar, and then we parse the sentence, we print out the results, and what we see here is that our grammar has identified 2 chunks, namely the little yellow dog and the cat, and the other things are outside of our noun phrase chunking. We can visualize this thing by typing result draw. So we have the result here, and it will give us a small tree where it says that here's a noun phrase chunk. Here's another noun phrase chunk. And then there are 2 other things, namely VBD, a verb, and in. I'm not sure why this is also in bold here, which are outside. And our first chunk consists of those 4 words, and our second chunk consists of 2 words. What we can do is we can define chunk rule grammars to describe possible chunk sequences, and we can define tag patterns. So part of speech tag patterns, right? So the simple pattern that we've seen before is determiner. So it doesn't have to have a determiner. It could have a determiner, and it could have 0 or more adjectives and then a noun. So this is a simple part of speech tag pattern that would identify NP chunks, but it would fail on many other NP chunks, such as trade figures, which starts with an NN and then an NNS. It would also miss any new policy measures. Why would it miss this? Because again, we have an NNS here, so this is, I think that's a noun in plural, right? It would also miss earlier stages, because earlier stages is like a JGR. So it's also an adjective, but it's a subtype of an adjective that is not matched by our regular expression here. It would also not match Panamanian dictator Manuel Noriega, because here we have a proper name in the end. So our pattern would miss many other cases. So we could refine our pattern to say, okay, it could have a determiner or not. It could have a JJ, and it could be even a subtype of JJ. It could be a subtype of an adjective, such as JJR. And there could be, again, 0 or more such patterns. And then finally, we could also have an NN, so that's a noun, and variants of NN, such as NNS or NNP, right? And this still would not be able to capture more complicated stuff like his Manson house speech, because Manson is his is a pronoun. It would also miss something like the price cutting, because maybe our part of speech tagger classifies cutting here as a verb, even though that's a little bit unclear what the tagger would do. Would the tagger label it as a verb or as a noun? So that's also what you see if you use such tag patterns. Then the quality of your chunking is a function of the quality of the part of speech tagging. If the part of speech tagging is not good, the chunking will also not be good. And of course, we focus here on noun phrase chunks, on NP chunks, because we want to detect entities, and entities are often parts of chunks. But we could do similar things for verb phrase chunks or adjective phrase chunks, right? And if we apply if we supply different patterns in our regular expression, such as the ones listed above. So we could say we have different patterns here. It could be one or more NNPs, or a noun phrase could consist of determiner or preposition together with adjective and noun. we would just list it like this in NLTK. So we say an NP is one of those different tag patterns. We then compile our regular expression and apply it to this sentence from above, like Rapunzel let down her long golden hair. We parse the sentence, then we would identify those two. And the important things is the chunking rules are applied in turn. So we check out whether this rule applies or not. And if it does not apply, we check out whether this rule applies. So they would be applied in sequential order. And the cool thing that we could do is we could explore a tagged corpus using such a grammar, right? So we can define our own little, let's say, chunking grammar, where we define our chunk that we are interested in to be a verb, something that is a verb or a subcategory of verb, then a form of to, like this TO has the part of speech tag to, and then another form of a verb. Then we go over the Brown corpus, we go over all the tagged sentences, we parse each sentence, and then we go into all the small little subtrees. The subtrees, what are the subtrees? These are these things here of the parsed sentence. So basically these are the individual chunks. And then we check whether those subtrees match to our chunking grammar that we've defined above, and if so, we print it out. So if we do that, we would find something like this, where we get all those patterns in all sentences. So one sentence could have multiple such patterns that tell us, okay, here's something that's like a verb, then we have to, and then we have another verb, such as combined to achieve, continue to place, serve to protect, wanted to wait. So if we define such little grammars, we can do shallow chunking and extract interesting grammatical constructions.